All right, let's start. Welcome to the colloquium. It's my great pleasure to introduce our speaker today, Robin Ding from Columbia University. And so Robin has really done a lot of exciting work at the intersection of AI and software engineering, specifically focusing on improving LLM's capabilities for complex software engineering tasks that go well beyond code completion, code generation. And so in that space, Robin is thinking about suitable model training with more enriched context, well beyond source code, and then also high-level reasoning about more complex questions like software design, cross-cutting concerns, where this richer context is really needed because it's not local in the source code itself. And if that wasn't enough, there's a lot more on evaluations. So Robin's work really pushing the boundaries there on proper evaluations, making sure that all the benchmark results that we're getting are indeed good proxies for what real-world deployments would look like. All right, so without further ado, let's welcome Robin. Thank you.
All right, thanks a lot for the great introduction. And I'm very honored to be here to share with you about my research in advancing language models from code generation towards the software engineering. So let me start from this question. So how many of you are still writing 100% of code on your own without the help of large models such as ChatGPT? Oh, there are a few. You guys are really hardcore programmers nowadays and give you my respect. So for myself, I always keep ChatGPT open on the side, and I will prompt it whenever I have a coding problem, which is quite amazing. And thanks to all these great AI coding assistants, I only write 50% of my own programs, and for the other 50%, I will either prompt or just tap. And this seems not only my personal situation, since as also addressed by leaders from the big tech companies, seems more and more AI-generated code will be eventually integrated into the realistic software as well. So probably at this moment, we're all on the same page that the AI-assisted coding is drastically revolutionizing how we write code every day. While we are celebrating the success of the automated code generation, as software engineers, they probably still have to ask, is this enough though? Is code generation all we need? And the answer is obviously no, because code generation is not exactly software engineering. So if we regard the software engineering as an iceberg, the code generation is just the most obvious step of it. So if we hope to achieve more advanced automation in software engineering, we probably have to check what is deeper into the sea. We definitely hope to achieve like very similar automation that we have seen in code generation, but to support a broader scope of software engineering tasks, such as debugging, execution reasoning, program repair, etc. And we also hope such automation to be realized in a trustworthy way, where the deployment of these automated tools could be reliable, secure, and also help the users to protect their private information. And with all these advancements we will achieve with LLMs, we would construct compound AI systems around these models to eventually approach the full stack automation that covers the whole cycle of the software engineering, from the development to the maintenance. Unfortunately, however, when people directly apply LLMs for the realistic software engineering tasks, they actually complain about these models. For example, people notice that while LLMs can automatically generate code, they cannot fully understand their own generated code. So whenever there's an issue, they could not effectively self-debug, which actually leaves actual burden for human developers to fix the LLM-generated issue. Also, LLMs can hallucinate code packages and misuse APIs, which actually leaves significant security concerns, and the usage of these unauthorized packages and APIs could be potentially exploited by attackers. And besides, the industry users have also complained that the AI-generated code could have very subtle security flaws that actually compromises the security of their software product. We are able to find some concrete evidence regarding these limitations. For example, if we give ChatGPT a very simple LeetCode problem, like a bitwise operation, it can generate a clean and concise solution. Good. But then, even with this simple problem, if we ask it to do a little bit more symbolic task that probably software engineers need to do every day, such as the unit test case generation, it fails. And the model we test here is actually O1, which has been trained with advanced general reasoning capabilities, but seems it is not effective enough yet to perform the symbolic reasoning regarding the program semantics. And this is not only my observations. Several other researchers have also identified such weaknesses of ChatGPT that they struggle to reason about the symbolic functional properties of programs, such as the code invariants, as well as their runtime behaviors. And beyond such a local symbolic reasoning for isolated programs, more global software reasoning is also required, since software is actually designed into modules, which maintains very complicated hierarchies and modular interactions. Here is an example that requires such a global software reasoning, where we prompt ChatGPT to validate the correctness of a very simple Python program to check whether the return value of this function is always a positive number using a third-party library called Crosshair. So Crosshair is basically an open source program analysis tool for Python. Unfortunately, however, we realized that ChatGPT cannot even generate an executable program for it. And the main reason for such a failure is the third-party library we're using, Crosshair, is a very low-resource PyPy packages, not as dominant as, say, NumPy. So ChatGPT does not know much about it. And without the global reasoning of the whole library of Crosshair, such as its code bases and documentations, ChatGPT tends to hallucinate a lot, including the modules to be imported, the API to be used, as well as the syntax that is required to trigger the backend symbolic tools. And we actually systematically studied this issue of ChatGPT, and it turns out that ChatGPT can only predict 10% of the API usages for those cases that require such a global software reasoning. Last but not least, as we have discussed earlier, LLMs also tend to have a very weak sense of code security. For example, here are two pieces of functions from Linux kernel. And as you can see, while these two functions share like tens of lines of code in common, missing a very subtle if check in the middle will lead to a security vulnerabilities of null pointer dereference. However, when we visualize the LLM's embedding of these two functions using the OpenAI embedding model, we realize that the LLMs could not effectively distinguish between these two functions because they are textually similar. However, this is definitely not what we want, since such a confusion will actually make LLMs struggle to tell apart the security vulnerabilities from the benign code, simply because they could not effectively draw a classification boundary between like two overlapped embeddings. I mean, this is actually very confusing, right? Like, why our LLMs are so capable at generating code while they have significant limitations for this kind of software reasoning? So to answer this question, we probably need to revisit how LLMs are pre-trained on top of code. So the first step of this pipeline is collecting data, where we collect tons of open source code files from the GitHub repositories, and then we flatten these code files into code tokens, and then we randomly group several files to construct a concatenated sequence to fill up the model's context length. And during training, we will actually train these models to auto-regressively predict the next token in this concatenated sequence from left to right. And when the training is done, we will prompt the model with an incomplete program or natural language instructions, and the model will complete the prompt accordingly. Finally, the LLMs will be systematically evaluated with the popular benchmarks, where the models will be prompted to complete a code function or code file, and their solutions will be evaluated against a set of predefined test suites. While this pipeline has successfully produced several code generation models, such as Codex from OpenAI and Columma from Meta, it has limitations by design for the comprehensive software reasoning. First, for data, the online code files are typically static code text and miss the annotation of its symbolic functional properties, such as the invariant code properties and the corresponding execution traces. And without seeing a lot of such signals, LLMs will struggle to really connect the static code text with its deeper program semantics. And also, the quality of the online code data could be rather noisy, where the malicious code could be directly memorized by the model during training without even noticing the danger. So later, the code generated by such models could be malicious as well. And during training, because of this random concatenation of code files, which are typically irrelevant to each other, predicting the next token in this concatenated sequence does not really teach LLMs to reason about the modular interactions and global software dependencies. In addition, because the model is trained to predict the code text, it also struggles to tell apart those textually similar sequences. While in code, a very subtle difference in a comparison operator could change the control flow and trigger the security vulnerabilities. And during inference, without access to the most up-to-date references, like the current code bases and documentations, the model could hallucinate and make very outdated predictions based on its internal but stale knowledge. What is even more unfortunate is that these popular benchmarks focus completely on the function or file-level code completion, failing to expose these weaknesses that we have discussed so far. So the LLM's developers could keep overlooking all these important software engineering perspectives when they work on the next generation of LLMs. So to advance LLMs towards the realistic software engineering tasks, my research focuses on enhancing their fundamental software reasoning capabilities through each step in this pipeline. To start with, I definitely hope to collect more code-specific symbolic signals rather than relying only on the static code text to train LLMs. So I perform program analysis to annotate the code syntax and underlying graph structures like the data and control flow, as well as the deeper functional properties, including both the static and the dynamic perspectives of the program semantics. And beyond the local program features, I also target the global reasoning of the software structures, where I curate the project-level data by performing dependency analysis over thousands of software projects to expose the software hierarchies and extract the modular interactions. And besides the general reasoning of software programs, security is another focus, where we crawl the publicly reported security flaws and analyze them for fine-grained annotations regarding their vulnerable patterns and evolving histories, like when and where they're reported and how they're patched. And then, as the next step, I customize the training to capture these enriched signals, where I propose training strategies and augment the learning objectives for LLMs to reason about the symbolic program features, both explicitly in the token space and implicitly in the latent space. In addition, for better global software reasoning, I also optimize the model architecture to incorporate broader software context in a flexible and efficient way, so that LLMs can effectively capture the cross-file dependencies and modular interactions. I further optimize the prompting strategy and construct systems around these models to further boost their inference time performance, encouraging them to statically reflect after the generation and keep improving the solution iteratively, and also equip them to dynamically interact with the symbolic tools to retrieve information and also validate the correctness of their own solutions. And finally, I construct new benchmarks and design new metrics to evaluate LLMs beyond just file or function level code generation, comprehensively assessing their consistency, global software reasoning capabilities, and security awareness under the realistic software development scenarios. And this is the very high-level overview of the research I have done so far. And as a result, my interdisciplinary research has been published in varied domains, including software engineering, programming languages, machine learning, and natural language processing. And the outcome of this research has contributed to both open source communities and companies. For example, my latest vulnerability detection benchmark, PrimeVol, has been integrated into the evaluation system of Gemini from Google DeepMind. And my another benchmark, the Crosscode Eval, has drawn the very early attention from LLMs developers regarding the importance of the global software reasoning. For example, DeepSeek was the first to utilize Crosscode Eval as their primary resource to evaluate and enhance their code models, DeepSeek Coder. And then eventually, cross-code eval becomes more popular to help with the development of more open source LLMs, such as StarCoder 2 from the BigCode and Qwen 2.5 from Alibaba. Additionally, our approaches to incorporate the security awareness and broad code context have been directly integrated into Amazon Q, improving the reliability and the robustness for the backbone LLMs of the product. So in the following of this talk, I will focus on discussing our major efforts in teaching LLMs to reason about the program's semantics and the software dependencies. Specifically, we will start by introducing how we train LLMs not only to generate code, but also reason about the symbolic and functional properties. Then we will go beyond such a local reasoning and train LLMs to capture the cross-file dependencies and the modular interactions for better global software reasoning. OK, now let's start from the first part. Recall that while LLMs are pretty capable at generating code, they struggle to reason about the symbolic program semantics, indicating there is still a gap between the neural models that are pretty effective at capturing the statistical distribution of data and the symbolic reasoning that is required for the software engineering practice. And one of the main reasons of such a gap is, as we have discussed earlier, there is not much data online for the neural models to learn about these symbolic reasoning signals. Traditional PLSE techniques actually have been very effective at these specialized analysis for program semantics, but they also suffer from several problems. For example, the dynamic analysis does not scale well, since the task coverage is always a challenge. And such execution-based approaches always have very high latencies and cannot be directly applied on top of partial code. And the static analysis, on the other hand, typically requires significant human efforts to write rules, which are typically hard-coded and not flexible enough to capture those fuzzy patterns. So my research targets to bridge the gap by training LLMs to perform the symbolic reasoning, so that we could scale such specialized program analysis without additional latency from the symbolic tools, while the analysis itself is also more flexible in the online setting to tolerate those noises from the user requests and can be immediately applied on top of partial or even inexecutable code. So to achieve this goal, we made several efforts in the LLM training paradigm, where we propose new training strategies, augment the learning objectives, and customize the model design to perform different types of symbolic reasoning for programs. And for the sake of time, we will only discuss the first approach in details and briefly cover the effectiveness of the other two approaches. Recall this LeetCode problem of the bitwise operation. And when we execute this ChatGPT-generated solution, we realize it is actually buggy, since the real output turns out to be 12, while the expected output is actually 6, because of this buggy line in the middle. This actually reminds us how human program, where they not only write code, but whenever there's an issue, they will engage in an iterative process of reflection that they review their implementation to identify those symbolic properties that are expected to hold true, and analyze the execution traces against these symbolic properties to identify those unexpected behaviors and understand why the bug happens. So if we would train LLMs to imitate such a symbolic reasoning process, they will also be able to self-debug and iteratively improve their own solutions. To do this, we propose SAMcoder. So the first key design of SAMcoder is we specify 4 types of semantics to be learned by LLMs, enabling them to not only generate code, but also reason about its symbolic properties. Approximate indicates those high-level intents that the program is about to achieve. And one simple example can be the functional specifications of a binary search. Structural refers to the source code itself, which actually implements the approximate semantics with algorithms and data structures. And abstract includes those properties and constraints that will be identified during the code review, which are expected to hold true regardless of the program inputs. For example, for binary search, the rightmost pointer of the search should always be no larger than the length of the array, and the array must be sorted before the search begins. And the operational captures the runtime behaviors of the programs, such as the execution traces with specific unit test cases that can be checked against the abstraction semantics. So to collect all these semantics for training, we need a lot of fully executable code so that we could perform dynamic analysis to extract the comprehensive signals. Therefore, we synthesize such a high-quality data set. You might wonder why we don't directly use the open source code for training. So the reason is, while crawling these code is cheap, scaling up their execution is both expensive and practically challenging. For example, here's a piece of human vision class that implements some search algorithms, but this class cannot be executed or traced at all, since the open source code typically requires individual configurations for testing and not always have unit test cases for every random code block. And the quality of these random code blocks is actually difficult to assess, since in many cases, we could not get the fine-grained specifications to really judge their correctness. Like in this case, the class does not even have any docstrings to specify what it does exactly, and without the unit test cases, we could not even validate the correctness either. Therefore, we implement a pipeline to synthesize the high-quality and executable code samples. The main idea here is we use the open source code as seed to inspire the LLM to synthesize problems of the realistic topics, but with a more narrow scope to ensure the executability. For example, the inexecutable search class we just saw could inspire the synthesis of a binary search problem, where the latter is much easier to be executed. Then we keep using LLMs to synthesize the solutions for the problem, and use symbolic tools to generate unit test cases to validate the correctness of these solutions, and only keep those high-quality ones that can pass all the test cases as our high-quality training data. With this pipeline, we collect PyX, a high-quality data set with sufficient executable code samples. However, while we're able to extract all the semantics with PyX, our preliminary study shows that simply dumping all these program semantics in this raw format will actually make the training very inefficient and difficult to scale up. Since, as you can see, these varied semantics actually have varied data formats and granularities, so that LLMs really struggle to align the relevant information across these multi-model program semantics, especially when dealing with the formal annotation of the abstract semantics and the execution traces that have a lot of irrelevant and redundant details. So to address this issue, we propose monologue reasoning that aligns the semantics with only natural language and source code, the two most dominant types of data in the LLM pre-training. So the first key design here is to teach LLMs to connect the varied code semantics with the source code itself through different granularities of alignment. Specifically, we start from the most coarse grain alignment to construct approximate semantics by summarizing the overall objectives of the whole program, and followed by the detailed explanation of how the objective is implemented concretely. Then we move to more fine-grained alignment, where we identify the symbolic properties and constraints for each code blocks and explain them in natural language. Like the entry code block of this binary search requires certain preconditions from the input, the while loop maintains invariant properties to ensure the search works as expected, and the return block defines the post conditions when the program terminates. We'll explain how we automatically annotate these monologues for training in a minute. And finally, we move to the most fine-grained alignment at line level, where we construct the operational semantics by explaining the executing effects line by line, but again, in natural language, similar to the mental execution that humans perform in their mind during the robot debugging. We further construct monologues to reason about the reversed effects of execution, similar to the reverse debugging features as we have seen in debuggers like GDB and LLDB. But this is trying to teach the LLMs about the abstract perspectives of the execution. For example, when the final state of the binary search is -1, which means the key is not found, the model needs to understand that there are potentially infinite possibilities of the input that can lead to these final states, which is basically any combination of an array and any other key that is not part of it will lead to this final state of key is not found. So the model needs to needs to conclude the initial state as an abstract constraints rather than concrete values. And with this bidirectional explanation, we teach LLMs to reason about code execution with both concretely and abstractly. So the second key design of monologue reasoning is to train LLMs to effectively reason about these aligned program semantics in an order from the high-level intent to the low-level details. To start with, we still train LLMs to write code to maintain these very fundamental capabilities. Then, we will further train the model to review its own implementations by summarizing the overall objectives of the whole program and explain the details, followed by identifying the key properties and constraints for each code block. And finally, self-debug by reasoning about the executing effects in a step-by-step manner for both forward and backward directions. Okay. So to train LLMs to perform such a monologue reasoning, we need to collect a lot of high-quality monologues. So we design a rejection sampling framework to perform the automatic data annotation with the strict quality control, where we start by prompting LLMs themselves to annotate the monologues while using carefully crafted instructions and few-shot examples to ensure the monologues following our design. And then we implement strict selection strategy for each type of these annotated monologues to validate their correctness, and only keep those validated ones as our high-quality training data. Since the whole system requires significant engineering efforts, we will not go into too much detail here, but feel free to ask questions at the end if you are curious about specific technology. Okay, now let's talk about the results. We start by evaluating SamCoder, an LLM with 6.7 billion parameters to perform the symbolic reasoning to predict the executing effects purely statically on two popular benchmarks. And as we can see, SamCoder beats all the baseline models of similar sizes with a large margin, and it can even outperform those industry models with 10 times more parameters in predicting the code runtime behaviors. We also compare our monologue reasoning with other reasoning methods, such as chain of thoughts, scratchpad reasoning, and raw execution traces, where we replace the monologue reasoning, where we replace the monologues in our training data with each type of these reasoning formats, and retrain SamCoder multiple times for each of them as a fair comparison. Since the proposed monologue reasoning specifies the important perspectives of the program semantics and smoothly align them at different granularities, we can see that it reasons about the code execution much more effectively than other reasoning baselines. We are also excited to see that SamCoder could effectively self-debug completely statically with the monologue reasoning. Recall this buggy solution of the bitwise operation generated by ChatGPT, and now let's prompt SamCoder to debug this code. We notice that SamCoder is able to accurately predict the unexpected return value of this buggy program by itself, without really executing the code. And more interestingly, with the reverse debugging capability, it carries the expected value of 6 and tries to deduce the expected previous program states all the way back, and successfully localize the discrepancy between the expected behaviors and the buggy execution. And this self-debugging also makes SamCoder more effective at statically refining its own solutions than baseline models, which is especially useful when the real execution is not an option. Like users only provide partial code for analysis when we serve a chatbot, or we have practical concerns or restrictions or security concerns for frequent execution during their online deployment. Finally, we also noticed that training with monologue reasoning, which was originally designed for code analysis, also results in outstanding code generation performance, which highlights the general value of learning the symbolic reasoning regarding the program semantics. Besides training LLMs to perform the symbolic reasoning explicitly in the token space, like we have seen in monologue reasoning that explains everything verbally, we have also explored training LLMs to learn symbolic code properties in the latent space for non-generative tasks. Due to the time restriction, I could not go into details of these methods, but I hope to quickly show you the results. We evaluated these latent symbolic reasoning approaches with a broad scope of non-generative software engineering tasks, including branch coverage and program states prediction, as well as the clone retrieval, code search, and vulnerability detection. In general, we observed that learning to reason about program semantics largely helps LLMs to perform better in software engineering tasks, significantly outperforming those LLMs that are only trained to predict code text. Okay, so far, we have introduced how we enable LLMs to reason about individual programs locally. Now, let's take the next step to train LLMs for more global software reasoning to understand the interactions and dependencies among the software modules. Recall the crosshair failure we have discussed at the very beginning, where ChatGPT hallucinates due to the lack of the global software context. Such kind of programming that needs to reason about the external modules is also known as the modular programming. So to systematically quantify LLM's limitation in modular programming, we start by constructing a benchmark for it, where we first implement static analysis tools and perform dependency analysis over thousands of open source repositories to identify samples that requires the global software reasoning, such as the code snippets with external dependencies. And then we further identify the usage of such dependencies and create the prompt and target accordingly. We also retrieve the ground truth cross-file context for each of these created samples. And in this case, the definition of the API to be used in the target will be retrieved so that we could evaluate how LLMs perform differently with and without the ground truth context. With this pipeline, we collect crosscode eval, a multilingual benchmark with over 10,000 modular programming samples. Now, we evaluate ChatGPT with crosscode eval and see how it performs. Not surprisingly, ChatGPT cannot handle such a modular programming without referring to the cross-file context. But what is really surprising is that even when the ground truth context is retrieved and prepended to the prompt, ChatGPT still tends to ignore it and keep hallucinating the predictions in many cases. So to explain why such an ignorance happens, let's recall the standard training pipeline of LLMs on source code, where the training code files are typically randomly ordered and concatenated for the next token prediction without the dependency analysis. So the cross-file dependencies could be separated pretty far away from each other. And due to the context length of the LLMs, such a long-range cross-file dependencies will not be directly learned during the next token prediction because of the sequence truncation. And on the other hand, the irrelevant code files are typically concatenated together, which misleads LLMs to learn the wrong signals that they should frequently ignore the surrounding files since they're typically irrelevant. And this is why, even if the cross-file context is retrieved and prepended, LLMs still don't understand how to leverage it. So to this end, we propose CocoaMIC to redesign the LLM's training strategy for the modular programming. We first perform dependency analysis for each training file and retrieve their cross-file context individually. And then we propose to keep these relevant information for the model's reference during the training to capture the global software dependencies. Now the question is, how do we perform such a training exactly? The most naive approach is directly concatenating all the retrieved context and prepending them to the current completing file. However, practically, this is very expensive because the computational cost, yes?
how do you know what is relevant?
Right.
Like,
So
the cross-file context the potential cross-file context is enormous.
yes.
So
In this case, what we do, the dependency analysis only for the import statements. This is specific for Python. Yes, and we will retrieve whatever they're importing, and we will retrieve them as the cross-file context.
won't the list of transitive imports be too large?
Yes, it is true. And that's why I will actually introduce the next limitation, and I will introduce our, yeah. Right. So basically, the first issue is that practically this kind of prepending is very expensive because the computational cost actually grows exponentially with the context length, and simply there's so much information in the retrieved context. And exactly conceptually, the information in the cross-file context could be quite sparse. Imagine you import a module that implements hundreds of APIs with thousands of lines of code, but what you really need to complete the current file is just a few API names. So it will be a waste of compute if we directly prepend all the cross-file context as concrete tokens. So to address these problems, we propose a neural architecture that extends the transformer's self-attention to jointly model in-file and the cross-file context. And our architecture starts by designing a cross-file context fusion, where the retrieved references are summarized in a compact embedding via a special summary token. And this allows the model to efficiently integrate the relevant cross-file information without overwhelming the computation. And this summary embedding is then mapped back as key vectors and value vectors at each transformer layer for later joint attention of the code generation process. So during the code generation, we extend the self-attention mechanism of the generation model so that at each layer, the model still attend to the keys and values from the concrete in-file tokens, while also jointly attend to those cross-file keys and values that are equivalent to just one token per reference. Where during fusion, the model learns to extract the relevant information into these summarized representations, so the token generation model does not need to explode its compute by redundantly processing the full content with tens of thousands of tokens. And with this joint attention, CocoaMake allows for more accurate modular programming in a compute-efficient way. Yes?
So then the cross-file tokens, how are those much larger?
Yes.
Than?
They will basically summarize, because there are so many tokens in the, for example, in the retrieved modules, and then we don't really know which one is more important than the others during this kind of dynamic code generation. So we realize, so the next slide is like we will actually train both the fusion modules and the code generation modules by connecting both two models, and then their weights will be optimized towards the next token prediction, so that they can flexibly design, figure out what are the important information to be fused into this summarized representation. Does that make sense? Yeah. All right. Okay, so to evaluate our approach, we pre-train an LLM with 350 million parameters on the code data from scratch with 3 different settings. Without the cross-file context, which is the standard LLM training strategy, prepending the cross-file context to the completing file as concrete tokens, which is the most naive approach that will waste a lot of compute, and CocoaMake. And we can see that CocoaMake is significantly more effective than the other 2 baselines. And together with my collaborators at Amazon, we're currently scaling up CocoaMake to tens of billions of parameters to improve the modular programming capabilities of the product LLM at Amazon Q. Finally, I would note that CocoaMake has 3 notable differences when compared with the standard encoder-decoder architecture. First, our fusion and generation are basically done by the same model, rather than having 2 separate sets for the encoder and decoder, making CocoaMake more effective in practice when scaling up the model size. And second, we fuse and jointly attend at each layer of the transformer to incorporate the homogeneous information, since different layers in LLMs will learn different knowledge, while the original encoder-decoder architecture refers only to the representations from the last layer of the encoder when generating tokens using the decoder. And third, we get rid of the complicated encoder-decoder attention and directly extend the self-attention instead. And empirically, the latter is not only simpler, but more effective. Throughout this talk, I have introduced my major contribution to teach LLMs to reason about software programs both locally and globally. And overall, my research aims to improve each step in the LLM pipeline to advance its capabilities for software engineering. Okay, now let's recall the iceberg of the software engineering we have discussed at the beginning. In general, the LLM-empowered automation is still on the very surface of this iceberg. My research has made the early efforts to push these models' capabilities further to touch upon more involved software engineering tasks. In the future, while we will keep improving LLM's capabilities to support more tasks, we also hope to go deeper in this iceberg to explore the trustworthy deployment of these models, ensuring the security, reliability, and privacy. And looking further ahead, my long-term vision is to achieve the full-stack automation with compound AI systems, which can autonomously manage the entire software life cycle from the development to the maintenance. Let's first talk about our short-term goal. Since there has been many challenges in trustworthy deployment of LLMs, where these models not only tend to generate insecure code, but also fail to reliably provide consistent responses to different forms of the same questions. In addition, those very large language models, such as ChatGPT, has raised significant concerns from the industry users regarding the data leakage of their commercial code and information, since these very large models could not be deployed privately, while small models are much more preferred here, since they can be easily customized for the private usage. All these challenges have motivated me to start exploring these different perspectives of the trustworthiness of code LLMs. For example, we have collected a vulnerability detection data set to analyze LLM's weaknesses in security analysis. And I am also currently leading a blue team called LineCoder in the Amazon Trusted AI Challenge, where we explore how to train LLMs with advanced security awareness and how to rigorously align them to minimize the risk of generating malicious code. Moving forward, I would keep exploring the trustworthy code generation as well as the training LLMs to make security analysis more efficiently, where we plan to teach these models to interact with the security analysis tools to learn from their feedback and the known vulnerable patterns. And for the reliability perspectives, we have explored the specialized code reasoning, as we have discussed in SAMcoder, to improve the model's robustness against different types of perturbations. And interestingly, as we have discussed before, we realized that training models to reason could make them parameter efficient, where a small model could perform even better than larger models in certain tasks. So this actually makes me very interested in training much smaller but domain expert models in the future that they can reliably solve certain tasks so that users could serve these models locally with very affordable cost, which ensures the effectiveness while providing guarantees to predict their private code and data. With the advanced capabilities and trustworthiness of LLMs we would achieve in the near future, the long-term goal of my research lies in constructing compound AI systems to achieve the full-stack automation that covers the whole life cycle of software development and maintenance. So inspired by the definition of automation level in self-driving car, let's also think about what we would achieve in software engineering to eventually approach the full-stack automation. I would define the first level of automation as the file or function level code completion, which can be achieved by LLMs that are trained only with predicting the next code token. Then the next level would be one step further, that the model will not only generate code as one-shot prediction, but keep self-improving. And my research has proposed several strategies to enable LLMs with these advanced reasoning capabilities. Then we expect larger scale automation where the AI systems can interact with the environment, use tools, and retrieve external information to perform project level analysis. And nowadays, the agentic systems are roughly at this stage, but with very narrow domain like GitHub issue solving, as we have seen in Sweetbench. So in the future, I am targeting to extend these agentic prototypes to reliably support broader tasks in a more general way. The fourth level of the automation that I'm targeting will be something we haven't reached yet, where the AI system can both implement and maintain the whole software feature, which requires probably more than one LLM agent with varied expertise, and the system trajectories should be carefully designed to ensure the effectiveness and efficiency. Ultimately, we hope to achieve the full stack automation that the AI system will autonomously manage the whole software lifecycle. This will be extremely challenging. From the AI side, we need to construct the hierarchical and collaborative agents like a group of software developers work together, where they have distinct roles and they need to communicate to figure out how to solve those very complex tasks. From the system building side, we need to handle nearly all the complexity that any large system would have, like how to optimize the distributed computing, how to handle the concurrency, how to design the workload routing with networking, etc. And in the coming maybe 10 years or more, I would be very excited to collaborate extensively with researchers from all the related domains like AI, PLSE, security, networking, and systems to eventually approach this ambitious goal together. Finally, I would like to thank my mentors and collaborators, and thank you so much for your time to listen to my talk.
Time for a couple of questions. I think the ceiling microphones will pick it up nicely. If you want the microphone, let me know. I'll bring it over. Yeah, go ahead.
So I have two questions. So first is a more level question. So in the example projects you listed, I think both of them propose lots of new techniques. And since there are lots of moving parts, do you know which of those techniques or which of those parts yields a larger gain compared to other parts?
Yes. So we actually have a very detailed application study in the paper about different modules that we created as part of the novelty. And for example, in the SAMCore paper, we really evaluate like different semantics, like how they have different impacts on the final code generation by removing one of the semantics out of the monologue trajectories, etc. So, but yeah, I didn't cover that here, but you can check the paper for more details about applications.
Story there. So if you move one of them, do you always see like there's a degradation?
Yes, there's always a decrease in terms of performance, but the magnitude, like how much they decrease, depends on the task. For example, in code generation, probably like the execution reasoning is not that important. But for self-debugging, if we remove the operational semantics, it will be a disaster. It will be basically not performing anymore. Yeah.
Okay. So my second question is that, so there are lots of existing research on all those fields you have touched. So could you sketch a little bit, like how are you going to, you said connecting to all those fields, but how are you going to leverage the existing research in those fields in your future research?
Yeah, so I guess the easiest way of combining all these kind of technologies is really to construct these kind of agentic systems. For example, we will teach these models how to interact with the symbolic tools, for example, for formal analysis or for verifications, rather than relying on the model themselves to do that, but try to enable them pretty similar to developers to really interact with all these kind of off-the-shelf tools. That's one example. And as I mentioned at the very end, I mean, we definitely need all the insights from the system building to really construct a very kind of large agentic systems, which are potentially could be deployed in say, cloud or somewhere else.
So are you mostly saying that it should be the case that LLM agents should be able to interact with the existing tools in the way that a human user interact with those tools.
It might not be necessary to be the human way. I mean, the reason is like maybe like machine have a more can figure out a more efficient way themselves that are more like friendly for themselves. But from our experiments, it's like bootstrapping these models to use tools in human way is always more effective than training them from scratch to interact with these tools. Yeah. And probably that's also why the reason, for example, if you read this paper, DeepSeek R1, they have two settings. One is that directly train the reinforcement learning from scratch. The other one is like you have a code start phase. You bootstrap these models, teach these models how to reason with the human annotated data. Yeah.
Okay, thank you.
Yes.
It came up at various points in your talk, sometimes explicitly, sometimes a little bit in the background, that LLM-generated code can sometimes introduce subtle bugs.
Right.
Human-generated code oftentimes also generates subtle bugs. Do we have any evidence yet on whether the kinds of subtle bugs are similar?
That's a very interesting question. So I don't have any concrete study on top of that, but my assumption will be they will be similar. The reason is that these models are mostly trained with the human written code. So mostly the errors that are made by human will be directly learned by the LM during the pre-training. Yeah. Yes.
So do you anticipate that a human will have to read every line of code written by an LLM in order to look for those subtle problems? Maybe particularly in high assurance scenarios?
Right. So I think human, by looking through each piece of code or generated by LLMs will be tedious, like it will be a lot of efforts, right? So I guess the better way is that if the models could validate the correctness of their own code automatically, that would be more ideal. And we're actually exploring different ways, for example, whether we could train these models to self-debug, so that, but with the assumption that there are some unit test cases. Also, like it will be very interesting to see like whether the model could, say, even verify their own generations by using the symbolic tools. Yeah, but I guess the part I'm covering is mostly for self-debugging with the assumption that test cases are there. But if, say, we could generate C-Daphne code, then the compiler can directly give you some feedback that whether your specifications really align with the programs. Yeah. Yes.
For some newly developed domain-specific languages, they might introduce some specific security issues, and we also don't have enough training data for those newly developed domain-specific languages.
That's true.
Well, these LM-added code generations do pretty well for those domain-specific language, and if not, like whether each domain-specific language have a unique LM training course.
Yes. So I guess there will be two questions. One is this kind of general capabilities of code generation. So for low resource programming languages, especially the very new one, for example, like probably 1 year ago, like Rust is very new, right? And in these cases, we do have some recipe to how to really train these models for these low resource programming languages. But for security perspective, it will be very difficult. Even for those most dominant languages like C, it is very difficult to rigorously align these models to only generate secure code. That's something we are working on. But I would distinguish this, like I would try to make them different between the general capabilities of code generation, which I believe we can do for the low resource languages. But for secure code generation, it will be very difficult even for the most dominant languages. Yeah. Yes.
So in the first part of the talk, you talked about training the code understanding model on a very high quality synthetically generated data set that was LLM generated. So I was wondering if that makes the model very reliant on seeing very high quality data. In reality, a lot of human generated code is not that high quality, has different coding styles. So did you take a look at the impact of that?
So you're saying, does the high quality of our data make a difference from the baseline models?
Yeah, and I guess does it make it harder to apply to human-generated code that might not have that, might have a different level of quality or style.
Yes. So I guess one of the most important thing nowadays is not only the quantity of data, it's also about the quality of data in terms of data annotation. So definitely, if we train the larger models on always on high quality data, it should always outperform those models trained on more but average quality of data. So that's actually something we're expecting. Yeah. But I guess in model log reasoning, the difference is not only the high quality data, but also the new semantics that we are adding back into the training, this kind of approximate semantics, abstract semantics, and the operational semantics. I think that will be the key part beyond the high quality data curation. Yeah.
So I also have a follow-up question.
Yes.
So you mentioned you spend 50% of time relying on LLM when you're coding and 50% code by yourself.
Right.
Since you're an expert in LLM-driven coding, which part you think LLM cannot help you? Why not 100% relying on LLM?
That's very interesting, right? So so the short answer is that if we regard programming has two modes, one is acceleration, where you have very specific, like you have very concrete specifications about what you want to do, and LLMs are pretty capable at accelerating, speeding up the whole programming practice. But the other thing the other mode is called exploration, where you need to probably design the software, you need to do abstractions at different levels, and this kind of exploration mode of programming, LLMs could not do that well. And one of the main reasons is that we don't have a lot of data to train the model about software design and different layers of abstractions. So I guess that's, for me, it's like I will be in charge of most like this kind of software design, abstractions, this kind of more creative stuff. And the LLMs will mostly help me to speed up what I'm sure about. And another thing I would mention is like there will be two extreme capabilities that LLMs have. One is that they are pretty capable at high-level programming, like this kind of data science-related Python code generation. The other extreme is, in this kind of data science code, the model is pretty capable. But for another level is like, another extreme is like this kind of kernel-related coding or system-level coding, like Linux kernel, CUDA kernel, or even compiler development. The model could not do that pretty well. So I guess that really distinguish when I will use larger models and when I will not. Yeah.
Thank you. If you have more questions, I would encourage you to find Robin and talk more about his work. And so with that, thanks Robin again.
Okay, thank you.